Once, the race for the stars was a contest reserved exclusively for nations. The roar of rockets belonged to the domain of governments, their flags emblazoned on the sides of mighty launch vehicles. NASA and Roscosmos defined the boundaries of what was possible, and the world watched as state-sponsored missions pushed the limits of human ingenuity. But all of that began to change in the early 21st century. In 2002, a private company dared to challenge the giants, a company whose ambitions seemed almost unthinkable at the time. That company was SpaceX. What began as an audacious startup has since transformed not only how rockets are built and flown, but the entire structure and philosophy of the global space industry. Today, SpaceX has done more than launch rockets. It has ignited an industrial revolution that's reverberated across every continent and every aerospace factory. In this exploration, we'll delve deep into how SpaceX's entrance into the market disrupted the status quo. We'll examine how rockets were manufactured before SpaceX and contrast that with SpaceX's groundbreaking methods. We'll unpack the technologies that enabled their success, from rapid prototyping to reusable boosters and 3D printed engines. We'll trace the global impact from NASA's own adoption of private spaceflight to a new wave of competitors and innovation. And finally, we'll look ahead. How is SpaceX's philosophy shaping the future of space travel and manufacturing itself? But first, let's turn back the clock to a time before private rockets, when the rules of the game were very, very different. For decades, the playbook for building rockets remained largely unchanged. In the 1980s, 1990s, and even into the early 2000s, the world's leading space agencies, NASA in the United States and Roscosmos in Russia, relied on complex, labor-intensive manufacturing processes. Every rocket was essentially a bespoke creation, painstakingly assembled by teams of highly specialized engineers and craftsmen. Components were sourced from a sprawling web of contractors, each contributing small but crucial parts to the finished vehicle. The result was a manufacturing process that was slow, expensive, and inherently inflexible. Building a single rocket could take years, with each stage requiring meticulous attention and manual labor. Rockets like the Space Shuttle or the Russian Soyuz were marvels of engineering, but they were also products of a bygone industrial age. Each component, from the engines to the tanks to the avionics, was built in small numbers and to exacting specifications, often requiring custom tooling and hand assembly. This approach came at an enormous cost. Launching a single mission frequently required an investment of between $100 million and $300 million. Worse still, nearly every rocket was designed for just one use. After their fiery ascent, the boosters and stages would fall back to Earth or burn up in the atmosphere, never to be recovered. It was as if every airplane or car were thrown away after a single trip. The economics were unsustainable, and the barriers to entry were immense. To play the game, you needed a government's budget and a nation's infrastructure. Enter SpaceX. From the very beginning, Elon Musk's vision for SpaceX was rooted in the idea that space could and should be accessible, affordable, and repeatable. To achieve that, every part of the old system would need to be reimagined. The company's first major breakthrough was the concept of reusability. For decades, the idea of landing and reusing rocket stages was considered impossible, or at best, impractical. But SpaceX made it a reality with the Falcon 9. In 2015, the world watched in awe as a Falcon 9 first stage booster descended from the edge of space, fired its engines, and landed upright on a pad near its launch site. Suddenly, the notion that rockets were disposable was obsolete. But reusability was only the tip of the iceberg. SpaceX also revolutionized how rockets are made. Traditionally, rocket manufacturers relied on a far-flung network of suppliers. SpaceX took a radically different approach. Through vertical integration, they committed to producing around 80% of every rocket in-house. Engines, tanks, avionics, and software all were designed and built under one roof. This approach slashed costs, improved quality control, and allowed for rapid iteration. Automation played a key role as well. SpaceX's factories in Hawthorne, California, and beyond hum with the activity of robots and advanced manufacturing equipment. The use of 3D printing, or additive manufacturing, has enabled the creation of complex rocket engine parts that would be difficult or impossible to fabricate using traditional methods. The Super Draco engines, designed for the Crew Dragon spacecraft's emergency abort system, are a prime example. These engines are 3D printed in a high-strength metal alloy, enabling intricate internal structures and rapid production cycles. Agility became a core value, In contrast to the years-long production timelines of legacy aerospace, SpaceX has embraced rapid prototyping and continuous improvement. New designs and upgrades are tested, refined, and implemented at breakneck speed. Failures are not hidden. They're analyzed, learned from, and turned into opportunities for improvement. This culture, borrowed from Silicon Valley's software industry, has enabled SpaceX to innovate at a pace that rivals cannot match. To truly understand the scale of this transformation, one must look inside SpaceX's manufacturing facilities. The company's main factory, located in Hawthorne, California, is a vast complex where raw materials enter one end and finished rockets emerge from the other. Here, aluminum-lithium alloys are transformed into fuel tanks and structural elements. Sheets of carbon fiber composites are molded and cured to create lightweight but incredibly strong fairings and interstages. Perhaps most striking is the engine manufacturing line. Instead of hand-built artisanal engines, SpaceX uses advanced machinery and 3D printing to produce the Merlin and Raptor engines with unprecedented speed and precision. The production floor is a blend of human expertise and robotic automation. Technicians oversee the process, but much of the heavy lifting, welding, machining, assembly is carried out by programmable machines guided by sophisticated software. All of this has led to a dramatic acceleration in production timelines. Where it once took years to build a single launch vehicle, SpaceX can now assemble and prepare a Falcon 9 rocket for reflight in as little as 21 days. This turnaround was unthinkable a decade ago. Not only does this speed reduce the cost per launch, it also enables a cadence of missions that would have been impossible under the old paradigm. The impact of SpaceX's innovations has rippled throughout the global aerospace industry. Even NASA, the very agency SpaceX once sought to challenge, has become a customer and partner. Through the Commercial Crew Program, NASA has entrusted the transportation of astronauts to the International Space Station, to SpaceX's Dragon spacecraft and Falcon 9 rockets. This marks a radical departure from the era when only government-built spacecraft carried astronauts to orbit. Other companies and agencies have taken notice. Blue Origin, founded by Jeff Bezos, has adopted many of the same manufacturing philosophies: vertical integration, reusability, and rapid iteration. Rocket Lab, a New Zealand-American startup, employs 3D printing extensively in its Rutherford engines. Even established players like ISRO in India and Ariane Group in Europe are rethinking their production strategies, incorporating automation, modularity, and digital design tools to remain competitive. Perhaps the most significant shift is the erosion of the government monopoly on space access. The door has been thrown open to private enterprise, and with it has come a flood of new entrants, investment, and ideas. The cost of getting to orbit has plummeted, and the frequency of launches has soared. Space is no longer a playground for superpowers alone. It's a frontier open to entrepreneurs, researchers, and even students. SpaceX's success has sparked a new era of competition and collaboration. Venture capital pours into space startups. Countries around the world invest in launch facilities and satellite networks. For the first time, space is becoming part of the global economy in a way that is decentralized, dynamic, and highly innovative. Looking ahead, SpaceX's ambitions show no sign of slowing. The company's next-generation vehicle, Starship, represents a further evolution of its manufacturing philosophy. Starship is built from stainless steel, a material chosen not only for its strength and resilience, but also for its ease of fabrication and rapid production. The goal is to produce Starships at a pace reminiscent of the automotive industry, rolling off assembly lines in numbers that dwarf anything seen before in aerospace. The rationale is simple. If humanity is to become a multiplanetary species, as SpaceX envisions, then rockets must be manufactured in bulk, quickly, affordably, and reliably. The idea of building a rocket as a handcrafted, one-of-a-kind machine is giving way to the concept of mass production. SpaceX is betting that the same principles that brought cars, planes, and computers to the masses can do the same for space travel. This shift is already having profound implications. As rockets become more like industrial products and less like bespoke projects, the barriers to access fall even further. The dream of routine, affordable, and sustainable spaceflight is coming into focus. The ripple effects are felt not just in the launch industry, but in satellite manufacturing, lunar exploration, and even the nascent field of space tourism. In summary, SpaceX has changed far more than just how rockets are launched. It has redefined how rockets are built. By challenging the assumptions of the past and embracing new technologies, production methods, and business models, SpaceX has set a new standard for the entire industry. The result is a world where space is more accessible, more competitive, and more exciting than ever before. But as we look to the future, the question remains: who will shape the destiny of space exploration? Will it be governments with their resources and experience? Or will private companies driven by innovation and ambition lead the way? What do you think? Will the future of space belong to the state or to the private pioneers? Let us know your thoughts in the comments. And don't forget to subscribe, leave a like, and click the bell so you never miss an update on the new space age. The next chapter is being written right now, and you could be a part of it.